There are a few different ways that energy can be transferred from one object to another. The first is simplest. It's called conduction. But conduction is what you get when objects are touching. So if you touch something hot, you feel, you might burn yourself, or it'll just feel warm. If you touch something cold, then you feel cold because and heat is flowing out of your body into the cold object. And objects are classified based on how conductive they are. Some are thermal conductors, and some are thermal insulators. And we have to put the word thermal before that because there are also electrical conductors and insulators. Often, what is a thermal insulator is also an electrical insulator, and vice versa, but not always. So thermal conductors, heat flows easily, and insulators, heat flows more difficultly. Is that a word? Difficultly? I don't know. I don't think that's a word, but we'll use it anyway. Heat flows more difficultly. It's harder to get heat to flow. Yeah. There are a few things related to heat flow. First off, the amount of heat that flows. One thing that is important is K, which is a property of the material called thermal conductivity. And it is a property of the substance. The next thing that's important, and all of these are very reasonable, it makes a lot of sense. Next is A, which is a cross-sectional area. And that makes sense that the bigger area you have touching, the more energy will be transferred through that area. Then we have a delta T, which also makes sense because the larger the change in temperature, the more heat is going to flow. And but we divide by L, which is our length, which makes sense. The longer something is, the harder it is for heat to flow through it. And then just throw in this T, time. The longer two things are touching, the more heat is going to flow. Now, this is we're making an assumption here. Really, this winds up being a differential equation, but we're assuming that the difference in temperature from one object to the other, or from one side of an object to another, is constant. Whereas in reality, it's probably going to be changing, and then this factor of time goes in, and it becomes an integral with respect to time instead of a just straight up multiplication. But we're not going to have to deal with that. And a lot of times, what you'll wind up calculating is the rate of heat transfer, which is a Q over T, energy over time, which, incidentally, an energy over time, that's a power, or has the same units of power. Remember, power was a rate of energy transfer. So that's an equation that we can use. For example, let's say we want to find the rate of heat transfer through a glass window that is 85 centimeters by 65 centimeters, and it's 9.1 millimeters thick. It's 25 degrees inside and 0 degrees outside. Well, there is a table in your book, and I didn't write down the page number. There's a table in your book that lists coefficients of thermal conductivity. So you can figure out where that is and consult it. On a test or quiz, I'll give you the different rates. Anyway, I have looked up that the thermal conductivity of the glass typically used in windows is about 0.96. So the rate of heat transfer, that's a Q over T, is 0.96. Let me move this up so you can see. Here's our equation. times the area, well, that's the cross-sectional area, which is the 85 centimeters times 65 centimeters, times the delta T, which is 25 degrees. And we're just finding how much energy is transferred, so we don't really care about whether it's 0 minus 25 or 25 minus 0. This L, the length, and in this case becomes the thickness of the window, which is 9.1 millimeters, 0.0091 time, and time, right. So that's the rate of heat transfer, which, when you punch it in, comes out to 1457.14, etc., joules per second. Joule per second is a watt. Yeah, so whichever units would be fine. And the problems can become more complicated than that, but we can do everything. We can have things like you've got a bar of metal, and then there's a something here, and these have two different temperatures. How much heat is flowing through that? And you could figure that out. One thing that's one interesting application of this is something that's commonly used, double-paned glass. It's actually used in most windows these days, anywhere that it gets fairly cold. Most windows are actually, there's a layer of glass, and there's a second layer of glass with air in between. So it's glass, air, glass. And by putting air, the coefficient of thermal conductivity of air is much less than the coefficient for glass. So by sandwiching this layer of air in there, it actually dramatically decreases the flow of heat out through the window. So double-pane glass insulates better, keeps your house warmer in the winter and cooler in the summer than it would if it was just a single pane of glass of the same thickness. The second way that heat can move from one place to another is called convection. Now, you might have heard of a convection oven, and the convection ovens do use this principle. Essentially, what convection is that you have a heat source. Let's say let's take the example of a stove. You're inside this little box, right? And you have a heat source down in the bottom, which I will represent with flames. Those aren't flames. Yes, beautiful flames. Okay. So there's heat down in the bottom. So the air down toward the bottom gets hot. And then as this air down in the bottom gets hot, it rises because it's less dense than the rest of the air. So the air rises up. And then the cool air from the top of the oven falls down, but now it's near the fire and it gets heated, and so it rises up, and it creates this little cycle of heat flowing, or well, not heat, but air or other fluid flowing around in this sort of circular pattern as the stuff near the heat source is heated, and then it moves away, and then the cooler stuff comes in, and it cycles around and around and around. This is one practical result of convection comes in with sea breezes. So if you're on the edge of the land, so here's say your land, and then there's water over here. When you're on a coast of a big lake or an ocean, this water I mentioned before has a high specific heat. This is our water. This is our land. And because the water has a high specific heat, it doesn't change temperature as much. So, for example, at night, when the sun goes down and it's getting colder, this water stays warmer night. The water's warmer, and the land cools down more quickly, so the land is cooler. So the air over here, above the water, being warmer, starts to rise, and then there's an empty space here, and so this cooler air from the land kind of moves out toward the water, and this hot air over here moves in to take its place and then cools, and so it creates this This is happening up very high, but at ground level, there then winds up being a breeze at night that goes from land out into the ocean or the lake. Then in the morning, the reverse happens. Everything is cooled down, and then as the sun comes up, the land heats up faster. So the land is hotter, and then the water is cooler, and then the reverse cycle happens, creating a breeze that you feel coming in from the water. Just an interesting little application of convection. There are also global convection patterns that have a pretty large effect on weather because there's a lot more warmth, there's a lot more thermal energy in the regions of the Earth near the equator that tends to then move toward the poles, and then that cooler air, comes down toward the equator, and it creates this little loop in that way as well.